So to review basically what we did yesterday, we took the specific example of QED where the matching conditions were to match the radial electric field and the radial magnetic field. And then we derived the ward identity and we showed that it was completely equivalent to the soft theorem. At least qualitatively, calculations are just details which you can work out. And some other conclusions from that we made was that the charge that you get from these matching conditions generate gauge transformations, large gauge transformations, and including these in the phase space means that you have an infinite degeneracy of vacua, and accounting for them in an S matrix can resolve the problem of infinite divergences and give you finite S matrices. And I think I also briefly at the end kind of show how it works in exactly the same way for super translations for gravity. But I've said the word super translations and super rotations quite a lot, but I haven't really explicitly said what they are. So let me do that, and then I'll go into super rotations and the stress tensor. So I think it's easiest to understand what is a super translation or super rotation in the original BMS or the original BMS paper. So I'm just going to follow what they did. So the idea is to look at any space-time and work in a Bondi gauge. So Bondi gauge or Bondi coordinates, which is UR and XA, and these are coordinates on S2. So I'm at the moment looking at 4-dimensional spacetimes. Oh, this UR. And the gauge is described by the gauge conditions G, R, R, and G, R, A, 0. And also the condition that del R so these are the gauge conditions you impose on the metric. And so this is, of course, for any space-time. I haven't said anything about asymptotically flat yet. And the conditions that define asymptotically flat spacetimes in particular are these fall off. So now so the GUU has to be -1. This is just a flat space answer. And then at large R needs to fall off like 1 over R. And then so this must be 1 over R squared. And GRR. So these are the only non-zero components. And gamma AB is the round metric on S2. Okay, so these are the conditions that define the class of spacetimes that I'm going to be studying, or that Bondi originally decided to study. And you might question these. That's completely valid, but they gave many motivations to study these class of spacetimes. And in fact, for instance, you can then go ahead and plug this into Einstein's equations. You know, just like we did for QED, and then solve it order by order in large R. And you'll find that the only data that needs to be prescribed is this coefficient right here. So it's RCAB, which I'm going to call CAB. And then everything else is basically given in terms of this via some sort of constraint equation. So for instance, there's this coefficient here is 1 over 32 R squared CAB. And I'm raising A and B indices with respect to gamma AB. This coefficient right here is 2 MB over R. And MB itself is not fixed, but the U derivative of MB is fixed via a constraint equation that I wrote yesterday. And similarly, this is also fixed. For instance, this is 1/2 dBCAB. So the point is everything is determined in terms of the CAB. And as I said, this CAB, or rather what's called the News tensor, and it's traceless because of this gauge condition. So it's a symmetric traceless tensor and describes the gravitational wave fluctuations.
CAB as a function of x.
And u, yeah. So I'm doing a large R expansion. So every one of these. So this is a function of u and x.
And NB is different.
No, MB is also a function generically of u and x. Yes.
These are CAB and x. Oh,
And that there's this constraint equation which relates the u derivative of MB with in this way 1/4. Let me call M over there. This is TUU2. So this TUU is the full gravitational stress tensor. In particular, it includes this matter part, but it also includes the gravitational energy. So this, for instance, is just equal to 1/8 NAB, NAB, and then there's a term that kind of corresponds to G, TUU matter, and I'm looking at the 1/r² component of that. So for instance, you might know this minus sign is kind of important. This is like one of the proofs that tells you that gravitational waves carry energy, because this means that if I integrate this entire equation over u, then this minus sign is telling me that, and since the stress tensor is always positive, this minus sign is telling me that the Bondi mass only decreases. The Bondi mass kind of is capturing the kind of the energy inside the space-time. So if gravitation.
What's the role of that 1/4 energy?
Oh, so that was here. My bad. This is not this. This is a different term. 1/4 dA, dB, and AB. So yes, the Bondi mass kind of describes the local energy density. The total energy, of course, is MB, then integrated over d2x. So then this term drops out because it's a total derivative. But see, this is precisely the linear soft graviton term that's important for our purposes. So when I'm considering the total energy, this term is completely unimportant. And this minus sign then tells you that this quantity decreases as a function of u. So this was the original analysis that told you that gravitational waves carry energy. Okay, so this is just kind of the definition of asymptotically flat spacetimes. And then how do you then use this to derive the BMS group? So I'm doing an asymptotic symmetry group analysis. So you might be familiar with this from ADS CFT, where you have to do this for ADS to determine the asymptotic symmetry group. But the idea is to just search for diffeomorphisms, psi, which preserve these boundary conditions, and of course the gauge conditions. So in particular, let me give just an example. The Lie derivative of GRR is required to be identically 0. But the Lie derivative of, let's say, GUU, you're not allowed to change the -1, but you can change this coefficient over here. So this is forced to be order 1/r. But you're not allowed to change this -1 because that's the class of spacetimes I'm working with. Okay, and then so on and so forth for every one of those g's, and then you can just solve all those equations. Here's the solution. So you can actually solve it exactly. And the solution takes the following form. And these e to the 2 beta and ua are just particular components of the metric. So this is actually, I should have said this, this is actually G, it's associated to GUA. So GUA is like GAB, UB. That's what I mean by this. And this is just GUR. Okay, so these are exact solutions, but as you note, the exact form of these psi's, so two things to note. Firstly, they only depend on two sets of functions. It depends on one function f of x, and it depends on a vector field y of x. So this is a vector field on the sphere, and it's a conformal killing vector. There's another equation. So this is a CKV on the sphere, and this is just any function on the sphere. So it's parameterized by, the total thing is parameterized by a function and a vector field. This is called super translations, and these ones are super rotations. The second thing to note is that the general form of psi clearly depends on the details of the metric. Like here you have to do a full integral, so you actually have to push yourself into the bulk. And so it's extremely complicated. The action of this thing in the bulk is extremely complicated. You have to compute this in generality. But if I push myself near the boundary, it's nice and universal in the sense that it doesn't depend in particular on the data CAB. Just near the boundary. So near the boundary, for instance, the super translation vector acts universally in the following way. And then, of course, there are subleading corrections in R, which do depend on the details. Not isometries. No, these are not isometries. As you see, I'm allowing GUU to be order 1 over R. So it's allowed to change this part of the metric. So this is not an isometry, but what it's doing is that it's taking you from one asymptotically flat solution to a different asymptotically flat solution. So you're staying within the class of asymptotically flat solutions, but moving between solutions. And preserving the gauge. But that's, yeah, that just tells me how I'm pushing in the diffeomorphism in the bulk. On S2, no, the conformal killing equation in two-dimensional S2 is just conformally flat. So there's an infinite number. That's where the Virasoro is coming from. But in higher dimensions, it's just the conformal killing on SD, which is finite. So this takes
slightly different forms.
yes.
Then
These would change. Yeah.
why do I
So that, again, you have to justify your fall-offs, and there are many reasons to, I mean, again, these are justified by just studying the class of interesting solutions, and it turns out that essentially all, like this captures gravitational waves, it captures black holes, all of them have these sort of fall-offs. So that's why you restrict to these interesting ones. Now you could certainly go ahead and say, I want to consider a larger class. That's totally acceptable to do. But the class we are studying here is this one. Yeah, the idea is to choose boundary conditions that are not so restrictive that all interesting solutions go away, and yet not so unrestrictive that you have weird sort of physics solutions that just are not doing the nice sort of things. And BMS spent like 15 pages in their paper justifying these ones, and then work from there. So these are, yes, absolutely. These change at MB and CAB, and I'll tell you how, for instance, you would get a different metric. Exactly. Like, I'll work that out. A super translated short cell is different from a short cell in a measurable way.
So if you make a boundary conditions more restrictive, that seems clear that it's
Yeah.
you throw away from step one. And if you make it less restrictive, can you say again what
You might,
qualities?
I don't know, I haven't really thought about, so there are some generalizations people do. Maybe I can point those out to you. So there are some generalizations where people, so for instance, one of the conditions here is that GAB, again, the point is that you're not allowed to touch this piece, so it can be order R. But some people say that, you know, you should generalize this to say that it's not just e to the gamma, that it's not the sphere, it's any metric. So this is another data. Then you would have the data CAB, And then gamma AB would also be data that you would have to prescribe.
Asymptotically locally ADS.
That would be asymptotically locally. Yeah, yeah.
And the analog in ADS would be
yeah.
asymptotically locally.
Yeah.
Yeah, that's interesting. And are there any, can that be filled in?
Yes.
That can be
Yeah,
in
yeah,
a
yeah,
smooth way
yeah.
table?
Yeah, yeah. So Barnish and Crozart have spent some time studying these generalizations.
So you
At
won't
least
get
this
flat.
one.
Yeah. So if you change that, you won't get flat spaces. You get some interesting.
Some other interesting things, yes,
Okay.
which they've studied.
But I was hoping that you could filter it completely.
Yeah,
In a non-singular.
yeah, yeah.
For instance, if you filter out like R square, I'm not sure. I was going to say, suppose I put an R square by n,
Mm-hmm.
then you might get something like conical deficit.
Yes, yes, yes. Yeah.
So you might expect that the generic thing would be to get
Yeah.
a singularity.
Yeah. So there are other types of singular. I'll talk about super rotations. They actually give you asymptotically locally flat spacetimes corresponding to cosmic string solutions, which I'll talk about. But okay, so to start with, at least those seem to be the nice outer boundary conditions. And once you fix those, these are your diffeomorphisms, and that's what I mean by super translation. This is what I mean by super rotation.
Sorry, just one more.
Yes.
Once we go near Krivlas, every solution is linearized. And we obey these boundary conditions. Then when we study the solutions near Krivlas, all the solutions are weak, right? We can use linearized.
They're weak, but you still have these interesting quadratic pieces. So this is all the way up at Scribe plus.
Good.
So it's not entirely linear.
Entirely linear.
Yeah.
But there's nothing, I mean, the linearized solution and then perturbing around that will give you accurate answers?
Yes, will give you, yes, exactly.
So basically the CAP then is just the amplitudes of various gravity waves.
Yes.
And M is the Coulomb part.
Yeah, or rather NAB is the gravity waves.
Yes.
Because CAB contains a zero mode piece. So for instance,
And,
yes.
And the fact that you have it in AB is simply the familiar fact that gravitational waves are transfer fusions.
yeah, they're symmetric traceless tensors of SOD minus 2. That's
And the fact that three-dimensional, sorry,
Yes.
it's just the equation. The gravity wave, omega is determined deficit.
Oh yeah, yeah, yeah. Like you have a p squared equal to 0, so it's dependent on 3 d minus 1 variables.
And one more thing.
Yes.
Sorry. So, if I told you what was happening at Scribe plus, that completely determines what's happening everywhere in space-time, including prime minus. This is complete data.
Up to super translations, yes. Yes, you have to include this matching condition. You see, because Einstein's equations are diffeomorphism invariant, right? So I can produce this. Yes. So here's the point. I can fix this data for you, and then push it into the bulk. But by the time you reach Scribe plus, by the time you reach Scribe minus, the data that you get on Scribe minus can only be determined up to some diffeomorphisms.
Okay.
And then to fix that, you need the matching conditions, and then that will also fix
Up to
that.
diffeomorphisms,
Yes.
this is the full data.
Yes.
And given any CAB,
Like I'm not being like CAB. You clearly need an integration constant here, and then there's a subleading integration constant here. That corresponds to super rotation. This one is super translations, and that's one.
the super rotation will once again be diffeomorph, right?
It's yeah. But up to these integration constants, those are
It's a real thing.
yes. So this integration constant, there's another integration constant here, which I didn't write it at this point. I'm going to write it for super rotation. So this GUA, the leading term is determined by equations of motion completely. Then there's a subleading term where part of it is this NA, which is called so this MB is called the Bondi mass aspect. This is the Bondi angular momentum aspect. And then these dots are completely determined in terms of CAB.
But the NA is if you conserve angular momentum.
Yeah, and then there's some equation for del U NA. So there's another integration constant here.
Conserve charges,
Yes,
and then there's this news.
yes.
And that, now if I give you arbitrary conserved charges and arbitrary news, is there some expectation that this will always can always be continued in the bulk into a non-singular thing?
No, that's where the Christodoulou-Kleinemann constraints come in, and they further impose constraints on what forms of CAB are allowed, so as to have non-singular solutions in the bulk.
And the form meaning that there isn't too much entity focus.
Yes, yes, yes,
So otherwise it's formula.
yes, yes, yes. So yeah, that's what CK's great work was, basically, that they managed to find these precise properties.
But if I'm going to live with black holes,
Yeah, that's not been worked out. What exactly, how much can we weaken it, weaken the CK constraints without doing too much damage? I mean, we want to do just enough damage to allow for black holes, but then.
as long as what would you expect physically? So, I'm sorry.
Yeah. No.
But physically, you accept that as long as you have finite energy.
Yeah.
And no blowing up energy densities, it's okay, right? Some gravity waves are happening. At worst, black holes.
Yeah. But those may not be the only ones of interest. Like, as I said, a super rotation of Minkowski spacetime, you can show to leading order in perturbation theory corresponds to a cosmic string solution, where you have one end of the string attached to Scri plus, it goes into the bulk, and then it attaches to another point on Scri plus. So this is a solution with infinite energy, because it's an infinitely long string. Oh, finite energy density. This probably has finite energy density.
Okay, thank you.
Yeah, I'm not really sure. It's a very difficult question to, especially because maybe I can answer. Maybe one could try to think of, but maybe if you're interested in black hole, like the non-linearities of GR make this question very hard to answer. Yeah. To be honest, I certainly don't understand even CK's analysis. I just know the results of their work. In fact, we'll see super rotations do not preserve the CK constraints. So they, again, because it's creating a cosmic string, now that we know that. So strictly speaking, to include super rotations in your phase space, you would have to weaken the CK constraints in some way.
And just one last, sorry, maybe a comment. This news kind of stuff looks like a subleading term. I mean, it looks roughly like in ADSC at least, it looks roughly like the boundary stress tensor.
The boundary stress tensor would be the next order, though. Not exactly this one.
Why
Right, because so in ADS, the boundary stress tensor appears at, so the analog of this would be at order 1 over r squared relative to the leading term.
I said boundary stress tensor in the sense that was independent data. But if you try to solve in power series,
Yes,
if I tell you what the boundary metric is,
yes.
then I have to independently specify what the boundary stress tensor is to go forward in a power series, in a ramp expansion. Here you have
Yes.
So it's
Yes. Actually, yes. In fact, it in fact also transforms very much like a 2D stress tensor with a Shortsian term.
Right.
But it seems it's not.
Isn't this the independent data you need to continue the solution? Suppose I wanted to solve this in power series.
Yeah, it is.
Now in ADS, arbitrary independent data usually leads to a singularity in the network.
Yeah.
And that's just a statement of stress tensor based on the equation of motion. I mean, it's
Yeah.
not just some arbitrary conservative. But here it doesn't, presumably does not, because you're only specifying in half of it.
No, but I thought in ADS was that there's the leading term, which is the data, and then there's another data at some sub-leading term, and if I independently choose them, you reach a reach a
Let's
singularity.
say the leading term is the boundary metric.
Yes.
Let's call that eta. Okay, I fix eta.
Yes.
Now, I try to go ahead and ramp an expansion at some term which is let's say z to the 4 and
Yes.
right?
Yes.
I need to specify another piece of data.
Correct.
This is the boundary stress.
Correct.
If I have these two, I can continue the power series of the.
Correct.
But typically this
Yeah.
leads to
Absolutely.
singularity.
Yes.
Here, it sounds to me like you're saying that typically does not lead to singularity. I mean, I don't consider black hole singular. And that's presumably because you're only doing half of space. Right, in ADS, you're doing it everywhere.
Yes.
So here you're only
You
doing
just
half of
just
space.
in
It's like the
advance.
past determining the future.
Correct.
It doesn't have the same flavor.
Correct.
Okay.
Yes, I think that makes sense. Okay. So basically, this very point that even though these diffeomorphisms are extremely complicated everywhere in the bulk, they take a very nice universal form on the boundary. And we've already seen now that going to the boundary means going to the infrared, going to the soft limit. This is kind of the reason why the soft limits are universal. And we'll see that the soft theorem corresponding to this one turns out to be the subleading soft graviton theorem. So maybe just for analogy, like let me say the transformation. So again, you can just take this zeta, plug it into, for instance, this equation, compute the order R term, and that will tell you how CAB is transforming. So you can check that the change in CAB, let's say under a super translation, just to begin with, is just F. So this term is exactly what you would expect, because you have an F del U. So this is exactly how if CAB was a proper tensor under these diffeomorphisms, that's how it would transform. But it's not, because it's GAB is a tensor, but this is some component of it. So it's not quite a tensor, and there's an inhomogeneous term which looks like right? So this is literally the exact analog of gauge transformations which when act on a gauge field del A, where now if I'm looking, this is gravity, which is like a non-abelian gauge theory. So let me just look at a non-abelian gauge field. So this would act like a covariant term, which if the gauge field were a covariant object, then you would have this transformation. But then there's an inhomogeneous piece, which is del A epsilon. So these two are exactly kind of very analogous. And we'll see that basically super translations are the gravity analogs of gauge transformations. And for instance, the symmetries for which this term vanishes are the global gauge transformations. Those are the ones you are familiar with. So the symmetries for which this term vanishes, you can solve this equation exactly. There are exactly 4 solutions, and those are the 4 translations that you're already familiar with. And so this is just a generalization of that. Okay. So that's all I wanted to say. And beyond that, I already said, so the thing that you have to match for the super translations thing is MB. This is what I talked about yesterday, very quickly. And you can show that the charge integral square plus minus F MB is precisely the charge. So this is what I call QF plus. So this is precisely the charge that generates this transformation, for instance, on CAB. And it's the charge, as I said, by studying the soft part, you can figure out what particular soft theorem is going to derive, and then the details and all I didn't work out, but they do, and it works out. It gives you precisely the leading soft theorem. Yes.
If these super translations or super rotations would change the solution in a drastic way, for example, in the cosmic string doctrine.
Super rotations do. Super translations are very nice.
Okay.
They don't really do anything.
Basically for the symmetry.
So I think maybe you can't exponentiate them, but like infinitesimally, they have something nice to say about, just like the full verse.
Changing, right? The reaction of these diagram.
Yeah.
The solution changes their nature quite a bit. So what is
Well, it preserves these things as required, but it changes the kind of the U fall-offs, which introduce. But this is also what happens with Virasoro. Like, it do a general Virasoro, it gives you some singularities at some point on the sphere. We usually don't care about it, but if I were to think of what's happening on the entire sphere, you would end up with some singularity somewhere, and that's what the cosmic string is. This is simply saying that the cosmic string induces a singularity somewhere on the sphere. That's what that super rotations is doing. And then you just solve the Einstein's equations to kind of figure out what that singularity is doing, and you'll just see the cosmic string appear by Einstein's equations. So that's really all that's happening. It's just what happens with Virasoro, picking out some singularity. But but again, just like what happens in Virasoro, if I'm only interested in a region where I can push the singularity outside, and then in some local region I can still deduce ward identities and stuff like that, and get interesting results.
I'm sorry, I
Yeah.
was taking out a little bit.
Yes.
But this N, in electromagnetism you have this large gauge transformation.
Yes.
There's one function which was a function only of the sphere, which was generating which was
Well, it's a function on the boundary, but the full gauge field, let me call that epsilon hat, u, x, r, the full gauge parameter is some complicated function, which of course depends on the gauge choice that you make in the bulk and blah, blah, blah. But the point is near Scri plus, it goes to a single function epsilon of x, just like what's happening here. But then into the bulk, when you push it into the bulk, it becomes some complicated function.
right. So there was sort of here you had these large gauge transformations, and there's a charge that you're
Yes.
And now you're saying that there are two things. Sorry, I
Yes.
maybe not answer you, but there was f of x and this y.
Yes.
And this I should think of as parameterizing large gauge, large coordinate surfaces.
Large diffeomorphisms. Yes.
And f of x is just a scalar function, y is a vector function on the sphere.
Yes.
And in the original BMS paper, y was something very special.
In the original BMS paper, they were really looking at the conformal group. They were looking at group transformations. They actually weren't looking at killing vectors. So they missed the local ones. So they only found the global CKVs.
Right. So their emphasis then was on the f of x.
Yes. So they focus on, and they and like 10 years after that has only been focused on super translations.
And you said f of x is the thing that gives you the soft theorem come from which of these?
Both of them.
Both.
So the f of x gives you the leading soft photon theorem. Y will give you the subleading one. That's what I'll talk about today. Yes, a subleading soft graviton theorem.
What comes out of conformal killing method?
No, y is a conformal killing. There was another equation. The y satisfies the conformal killing vector equation.
So this is the conformal killing vector from the point to the boundary.
With respect to this sphere metric, gamma AB.
Means that by conformal killing vector, I understand, after transforming it, you get the measure times some function.
Yes.
Okay, but this
Yeah. So
this is not supposed to change.
it's not. So if you look at actually what's happening, so let me say this piece has a YA, so it's going to act on gamma and give you a conformal factor, and this zeta R has this piece which is going to give you, with a multiplied by R, so that basically rescales R and kills off the conformal factor. So the GAB remains unchanged, but it acts on gamma as a conformal transformation.
Second term is motivated because actual
Exactly. I mean, that's where this conformal killing equation constraint comes in from, that leading term is fixed.
Can be fixed.
The only way it can be fixed, really, is that if I do, if I do some transformation here, that can be removed by scaling here. That the only possibility for that is a conformal killing, is a conformal transformation. Okay, any questions? So yesterday I motivated that super translations is associated to the leading soft graviton theorem. So I won't go into that again. And the brief point is just to basically look at this piece. So okay, maybe let me actually just quickly do this. So this is the charge. So you match MB, and you construct this charge. And in essence, just like we've been doing previously, you write it as a U integral over all of Scri plus, and then basically this becomes del U MB with some F, and then this is integrated over d2x. And the way to kind of figure out that it's going to be associated to the leading soft graviton mode is to just basically study this piece. So if I study this piece, del U MB, by this constraint, it has this linear piece, and then there's some bunch of quadratic terms. Let me just forget about that for the moment and just look at this linear piece. So this very first linear piece essentially has the form that is dA dBF integral du del u c ab, and then there's an integral over d2x plus quadratic terms. So this is going to be the soft charge, right? So it's going to be the thing that's supposed to insert a soft mode. And just like in the gauge field, what is this? This is the u derivative of the gauge field. And then you integrate over all of u. So I can think of this as e to the I omega u, and then with the limit of omega goes to 0. Right? So the u derivative pulls down a factor of omega, which kills the pole. And then you take the omega goes to 0 limit, and therefore, clearly what this object is doing is extracting the pole of the of Weinberg's soft graviton theorem. And then the check is to confirm that the rest of these quadratic terms do exactly what's needed to be done to give you the right hand side of the soft graviton theorem, and they do. Again, yeah, you have to choose f of x to be 1 over z minus w. So it's very similar to the QED case. Okay.
So, and
Yes.
in higher dimensions,
Yeah.
the SO whatever, the conformal transformations of the higher dimensional sphere.
Yes.
So what charge is that? Is that the Lorentz group?
Those are just the Lorentz groups. So just yeah. So the conformal group in d minus 2 dimensions is just SO1 comma d minus 1. That's the Lorentz group in d dimensions. But this is actually not fully understood because the subleading soft graviton theorem is a dimension independent statement. So clearly there must be some sort of superrotations, which must mean that maybe we have to relax the choice of boundary conditions so as to give you other. And there have been works on this where people have basically shown that there's a way to relax these boundary conditions such that instead of getting CKVs, you get any diffeomorphism. So Y is a completely arbitrary vector field. And then on the d minus 2 dimensional sphere. And then that's the thing that you would use to derive all the Ward identities, and everything would work out in that. Yeah. Okay. So superrotation. So let me now focus more on superrotations. So superrotations are basically these vector fields where I set f to 0. I just have this. So near the boundary, it takes a very general form that looks like this. And as I said, there's this extra term, there's this thing called the angular momentum aspect, which appears in the subleading large R expansion of GUA, which remember to leading order was something like 1 over, and then there's a 1 over R component, which is this NA. And I'm not writing this here, but all of these are determined completely in terms of CAB. And then this itself satisfies a certain equation, which let me just kind of briefly write it as dz squared. And again, it's not going to be important, the details, plus some quadratic terms. Okay, so as usual, you have the matching condition. So let me call this NZ minus. And then again, so there's two ways to do this. Here you already know the symmetry that you're interested in. So you can use canonical quantization and just construct the charges that generates this symmetry, which will of course give you the same thing that I'm talking about there. Another way to look at the same thing is to forget about the symmetry and just use the matching condition to construct the charges. And you'll then use once you have the charges, you can ask what symmetry does it generate, and it's going to be superrotation. So just like we did before, take your favorite vector field, as long as it's antipodally matched, and then you just construct the charge qy plus, which is just an integral over scribe plus minus of the sky. And then is T2Z. See, the thing from this construction, the thing that's nice about this construction is that here I do not have to say that y is a conformal killing vector. This would actually construct for me the general charge, which generates, so it would not necessarily correspond to these superrotations, it would generate the more general transformations. But they would not be what BMS would call superrotations. They would be the ones that more recent papers have said is the correct, you have to enlarge your boundary conditions so as to allow for all these diffeomorphisms. So that's why I think the matching conditions in basically all cases is more general. Like again here, I want to mention again that the only reason I was able to deduce the symmetry first is because I know how it goes into the bulk. I know that it's a diffeomorphism, and I know how diffeomorphisms act, and I know GR has diffeomorphism invariance, so I can just ask what are the set of large diffeomorphisms. But there are many cases of asymptotic symmetries for which there is no bulk description. I haven't presented any example here because gauge transformations and diffeomorphisms both have bulk descriptions. But I can give you another simple example is like there's a magnetic gauge transformation which on the boundary near on square plus, the electric U1 and the magnetic U1 both act on the gauge field in a very simple way. But we know that in the bulk, there is no description in which both the magnetic and the electric ones manifest. Either the electric will be manifest and then the magnetic is some crazy non-local thing, or the inverse. And similarly, there's a Soft-Fortino theorem which gives you a fermionic gauge symmetry. And this is Soft-Fortino theorem with global supersymmetry. So you don't expect any local symmetry suddenly to appear. But you see the asymptotic symmetry associated to that is a local fermionic gauge symmetry. But there's no manifestation of that in the bulk. So that's why these matching conditions are more general, because even if the symmetry is not manifested at the level of the action or local fields or whatnot, this is because here I'm only caring about S matrices in asymptotic states. So as long as the symmetry has a nice action on asymptotic states, the matching conditions will see that. Okay. Excuse me. Okay. So that's the chart, and the matching condition tells me that there's an equivalent charge on.
The Ashok's covariantization produced also the competing cross theorem in other cases.
Yes, because he was also looking at all diffeomorphisms. His symmetry is all diffeomorphisms at the end of the day. I think that is the correct boundary condition that you have to use.
About that, can't you just check whether the way you presented it last time, the boundary conditions were those that were obeyed by a Green's function, at least in perturbation theory.
Yes.
Can't you just
Yes.
check whether the Green's function has the larger matching?
No, they will certainly. So the relaxation that you have to do, for instance, to get all diffeomorphisms, is not changing the large R behavior. It's changing what you're allowing to fluctuate in the space of solutions that you're looking at. So in particular, I said that I'm defining asymptotically flat spacetimes with R squared times gamma AB, where gamma is fixed to be the metric on the sphere. That's what forced me to for CKVs.
Right.
If I don't fix that and I say I'm also allowing gamma to fluctuate, then I get all diffeomorphisms.
But can I check whether if I send in a bunch of parameters,
Yeah.
and I want to see what's coming out, I can do that by convoluting with Green functions,
That yes.
and so I can check whether the gamma ever changes, at least in such solutions.
Yes.
And you know what the answer is, yes or no?
I don't know the answer, but I don't think you'll see anything.
You probably know.
You won't see any change.
So for reasonable physical solutions, it doesn't look like you need that explanation. But maybe for
Yeah.
formal purposes.
Yeah. Yeah.
Before you see that, can you expand more on the statement that the magnetic field
So literally the magnetic and electric gauge symmetry acts on the gauge field on the boundary So this is the leading coefficient of AZ. So this was the electric gauge transformation. So the magnetic one just acts as, so it's just del Z. So this was the electric one. And the magnetic one just puts in an I, and that's magnetic one. So it just complexifies our epsilon parameter. That's it. So you just allow for this complexification, and you then included the magnetic one also.
And that is produced by the XZ of a bar.
Yes, exactly. Exactly. But if I try to push this one into the bulk, that's going to be non-local. Well, you'll have to complexify the gauge field. Yes, then you could do that. But the magnetic U1 that you think of is just some non-local action on the vector field, on the electric vector field, and then some. I don't know if it has to do with that. Because I'm thinking of, let's say I'm thinking the non-abelian analog of this, where I can think of the action of these symmetries on the field strength, and it's non-trivial. Then I don't have to fix a gauge or anything, right? Then it's still true that the electric and magnetic symmetries cannot be described on the same field strength. You have to go to the dual basis to describe, and it's non-local. So then that's not an issue of gauge fixing, I believe. I think. Yeah.
But in the bulk, there is one usually does not think of magnetic gauge transformations as a complexified.
No, it's not. It's some non-local. It's a very non-local action. But it localizes in the, just like a lot of things localize when I go far away. It happens to localize here as well. Yeah, it's just literally I can solve up to an integral. I can write the dual field in terms of the magnetic gauge field in terms of the electric gauge field. Just push up that integral thing to infinity, to square plus, and the integral collapses. And then get some nice local relationship. So like in particular, AZ dual 0 is I times AZ 0, right? This nice local relationship exists. Yes. Okay.
Since the agreement is the notion that one can combine electric and magnetic charge to form a
I see. I see.
spatial version of what.
I see. Okay.
So for the symmetries that cannot be pushed into the bulk, you won't have a covariant integration X2.
Cannot be pushed nicely into the, yes, then you won't have this sort of BMS sort of proof. Yeah, for the Fortino.
Kind of
no.
proof.
Yeah,
Would
yeah.
people do this?
Yeah, because these symmetries are, well, okay, there could be many possibilities. It could be that the symmetry, it is a symmetry of the action, but it's just some highly non-local symmetry of the action. It could also be that it's just not a symmetry of the action at all. It's just a symmetry of S matrices. I don't know which one of these is true. So if it was the first one, then you could probably still do it with Ashok's method. We just have to worry about extremely non-local symmetries and work with those. But if it's not a symmetry of the action at all, but only happens to be a symmetry of the S matrix, then it won't work. Excuse me. okay, so very briefly, it's kind of, you now you now know the way to go. Write it as a U integral over all of square plus. So this gives some integral over square plus. Du t to z, and then use the constraint equation. So again, just to justify to you that it's going to correspond to the subleading guy, let me just focus on the linear piece. And yes,
This magnetic thing, what kind of soft theorem does it derive?
the magnetic soft theorem. So there's a magnetic generalization of the leading soft photon theorem.
Which says what now?
Oh, it's just literally the same, where you take the electric charge of a particle and add to it the magnetic charge.
So the
Just the-
soft theorem has additional insertion of some soft theorem.
So you have to consider an S matrix with magnetically charged particles as well as electrically charged particles, and
But the theorem will insert a soft theorem.
the theorem is exactly the theorem is exactly the
Is
same.
is the photon the same photon? As
Oh, the photon is the same photon. Yeah. Yes. Yeah, and the soft photon is
There's
just
only one photon.
yeah. There's one photon, but now you have magnetically plus, or you can have
And the two polarizations are still related but not equal.
not equal. No, they're not related at all. Now they're independent degrees of freedom.
No, but there's only. No, I think what you're going to say. There are only two polarizations.
Oh, there are only two polarizations.
So what you call the polarization of an electric photon may be nonlinear,
Yes.
Linear combination of what you
Yes.
call the polarization.
But unlike in the purely electric case where there was only one soft polarization, now there are two soft polarizations, as expected. Okay. Okay, so let me just focus on the linear term just to like justify everything I'm saying.
Sorry, this magnetic stuff has,
Yes.
you said this a lot, this in higher dimensions, fairly analog of magnetic stuff.
Not that I know of. No. Yeah. Okay. So for instance, this looks like, again, I'm being very vague about numbers and stuff. D to z, dz cube yz, and then there's an integral over du of czz. Right? That's basically the kind of structure I get. I mean, I've integrated by parts multiple times and not kept track of signs and stuff. Okay, so basically it's clear that it's this mode, C upper ZZ. Which is important because when I lower them, I get C Z bar. So the holomorphic superrotations is associated with negative helicity soft graviton theorem. Right? Okay, so just to this mode, I can write as I can just write this as 1 or del omega u c z c upper z z, and then a limit of omega goes to 0. Yeah, I think that's right. Yeah. Right, so so omega, omega e to the I omega u, I can write as del u, and then integrate that by parts, so I'll get a del u acting on this. And then the del omega acting on that will pull down a factor of u. And then I can take the omega goes to 0 limit. So this thing will basically is equal to u del u c z z. And then I can integrate by parts and u, and I get that thing. But this is precisely picking out the subleading mode, because now this guy generates, so there's no u derivative anymore. So this guy generates precisely a graviton of energy omega. You multiply by omega to get rid of the pole. Not rid of the pole, but you've now put it to order 1. But then you take an omega derivative, which gets rid of the pole. And the order 1 piece, which after multiplying by omega became order omega, you take a derivative, becomes order 1. then you take omega to 0 to kill off all the higher order terms. Right? That makes sense? So 1 over omega, soft graviton plus subleading soft graviton. That's the structure. What I've done is multiply by omega and then plus order omega square. Order omega. Multiply by omega, then take del omega, right? So that kills off everything except for this piece. So clearly this operator is precisely picking out exactly the subleading soft mode. And again, I won't bore you with the details. The next part of the check is to just check that the quadratic pieces do all the right things so as to give you the right-hand side of the subleading soft graviton theorem. So let me at least tell you what the subleading soft graviton theorem is, because you may not have seen it. The subleading soft graviton theorem is actually probably interesting because it was not known before. It was actually derived only in 2014. And it was only derived because we knew superrotations existed. Like a nice example of where the knowledge of asymptotic symmetries help us find a new soft theorem that was not previously known. So the subleading soft graviton theorem is again, this is the operator that kills the pole. And this is a graviton with helicity alpha and some arbitrary in and out states. And this object S1, let me not say minus S1. Right. So this is the angular momentum operator acting on the kth particle. So in particular, it's the orbital plus spin. That's the gravitation polarization of the graviton with polarization alpha. Okay. So in particular, note that this is a differential operator. It's not a number, unlike all the soft theorems that we've seen so far. It's a operator that acts on this S matrix in some non-trivial way. Another example where I didn't talk about it, but where you should expect to see it is the soft Fortino theorem, because the Fortino is a fermion. So when I push it to being soft, you are left with an amplitude with an odd number of fermions. So the soft factor must be a fermion changing, statistics changing operator that acts on the S matrix to give you something non-zero. Okay, and just like it happens, I didn't mention this at all. Maybe you know this, is that gauge invariance of the leading soft theorem gives you momentum conservation, which is to say that if I replace epsilon mu nu with lambda mu q nu symmetrized, right? Doing this in the leading soft graviton theorem gives you momentum conservation. That's how Weinberg got momentum conservation in his original paper. Or if I take the soft photon theorem and replace the photon mu with some arbitrary lambda times q mu, then you get charge conservation. Similarly, for the subleading one, if I do the same insertion, you get angular momentum conservation as expected. It's trivial. You get 0. Well, no. Well, Fortino does not have any local gauge invariance. It's not associated to any local gauge. Yeah.
One could have derived subleading software.
Oh, absolutely. Absolutely. I mean, it was derived at the end of the day. I mean, once you know that, if you want to really check, you want to derive it by independent methods. And, well, it was first derived by Cacciazzo, who used some very complicated amplitudes methods to derive it. And then there's a much nicer method, I think, which does use some assumptions, but it kind of uses gauge invariance and knowledge of the leading soft graviton theorem. You can derive the subleading one. So there are independent checks that this is true.
There's also Ashok.
There's also a Stokes derivation.
I mean, but didn't go and talk anything about the boundary,
Absolutely, absolutely,
some basic analysis.
absolutely, absolutely. You don't have to do all of this.
Ashok, we haven't talked about it.
Yeah.
Yes. Yeah. It was only nice because no one had noticed that there even should exist something like this until superrotations was studied. But once you know that, then of course, obviously people have studied quantum field theories for much longer and have many more tools there to.
No, I'm speaking number of parameters which would specify your soft data at the boundary. Sort of tells you how many subleadings or leadings.
Exactly. Yeah. Yeah. Let me also say a few words about, for instance, the subleading soft photon theorem, which also exists, but is not universal in the sense that it does depend on a few details of the theory. Depends on like the first non-minimal coupling of the theory. And it's very easy to actually see where this is coming from if you know where the symmetry is. So the symmetry associated to the subleading soft theorem is basically also gauge symmetry, but it's a gauge parameter that instead of going to a finite value at square plus, it diverges. It grows linearly in R. But what that does is that if I try to construct the charge for that object, the gauge parameter is growing linearly in R. So when I epsilon times FUR, that's always going to be the charge that generates gauge symmetry. It couples to a subleading term in FUR because there's a R that grows. Then it has to be 1 over R cube to get a 1 over R square that will cancel the growth of the measure, right? So it couples to a subleading term in FUR. But as we have seen here, subleading terms care about a little bit more details of the theory and of the solution that you're interested in. And in exactly this way, you can see it kind of cares a little bit about not exactly what's happening at the boundary, but when you push yourself a little bit in. And from the action perspective, that just means that when I go to one higher order in derivative. So that's all there is. In that sense, you can keep going. The sub-subleading theorem will be totally non-universal, but in a given theory, it will only care about like the up to second derivative order.
This subleading soft theorem is obtained by considering the phi as
You don't have to. See, at the level of an amplitude or word identity, I'm only interested in the value of this vector field at finite number of points. And so then it doesn't matter, because if I tell you the value of a vector field at finite number of points, I can extend it globally on the sphere in a holomorphic way, but I can also extend it in a completely arbitrary way. So I can actually construct any vector field whose value takes some specific values at some finite number of points. So at the level of, finite number, correlation functions with finite number of points, there's no distinction between, at least the word identity cannot distinguish between a CKV and a generic vector field.
You can relate this to the discussion once you say that, constraint higher derivative term using causality. So we have some high derivative zero gravity, we derive a soft theorem from among the soft theorem should be that.
Would it be bad? I can.
Maybe the next question is, have you used, how much of the structure of Einstein gravity do you use for your stuff? So the Gaussian internal, how is the theorem changed?
Let me see. So this is completely independent of Einstein gravity. So this is Einstein gravity determines this equation. So I've used that. So these matching conditions still hold. those exact, these don't care about Einstein. You could, these just care about the fact that it's asymptotically flat. Yeah, I've used this constraint equation, which comes from Einstein gravity.
It would take you from one Einstein solution to another.
It takes you from any solution. It doesn't have to be Einstein. No matter what bulk gravity you have, it could be with any number of higher derivative terms.
Yeah,
One solution to a, let me just say one space-time to a different space-time. Doesn't even have to be a solution to anything.
I was just wondering, from the point of view of covariantization, I haven't said anything but what my diagram. But sounds to me, from that point of view, like the universal soft theorem is just be independent of that. That's all.
Yeah, Yes. Here's why. So what are the things that would change if I added some other higher derivative term? So you might guess that some terms will change here, maybe. But what will also change then is the canonical, when you canonically quantize, and therefore that will also change the commutators. But what will stay fixed is the commutator of Q acting on a field, because that's just a diffeomorphism. That's always a diffeomorphism, no matter what field you're sitting in. So Q might change, the commutator might change, but the Q commutator with any field phi will change. And that's all the soft theorem cares about, is how Q acts on a Hart state, which is the diffeomorphism on the Hart state, which is the right-hand side.
And so it will not depend on
So it will not.
the
Yes.
universal line.
Yes.
Now, of course, the ambiguity when you have higher derivative terms is covariantized with respect to which metric?
Yes.
Because you could covariantize with respect to G mu nu, or G mu nu plus
Yes.
some complicated harmony or something like that. But all those enter at the same order in which covariantization is ambiguous anyway.
Correct.
So the universal paths look like typical ones.
Yes. And that's what so the sub-subleading soft graviton theorem contains a universal part, and then there's some ambiguity which depends on higher derivative
And that
terms.
will depend on dynamics.
Yes.
And everything but the first two just one.
Yes. Okay, I did want to talk about black holes, but before I want to do that, I just wanted to say I started this entire thing by saying that I would like to write S matrices as correlation functions. I haven't done that at all here. So let me just quickly just do that and construct the stress tensor whose insertions will give you the correlation functions. Whose insertions in a correlation function take the usual form of a 2D stress tensor. So it's actually very easy to construct. You just need to know where to look. So the stress tensor, it generates diffeomorphisms, right? So, and we already know that the superrotation charge that we wrote down, it generates diffeomorphisms. In other words, what was the Ward identity? The Ward identity is always of the following form. You have some charge with the soft part on this side, and this is equal to the hard part of that charge, which appears on this side. But we know that QH acts on all the states to generate the symmetry on that state, right? So this side is literally just the symmetry transformation on that state. So the soft part of the charge should be is the thing that's associated to the current that you want to construct. In particular, it's the charge that you would have constructed from the current, right? So for instance, in the photon case, here, the soft part of the charge, of the gate charge, this, was just 4 pi over E squared and remember this NZ is not the same NZ. That's the angular momentum tensor. This is just the zero mode of FUZ0, right? And in a CFT, the charge that generates holomorphic Gates transformations is just, you determine it by just doing a contour integral with the holomorphic epsilon and the current Jz. So this tells you, so if I'm taking epsilon to be holomorphic, this z bar can be pulled out, it's a total derivative, and then this just becomes a contour integral over z. So then I can just match. Jz clearly has to be 4 pi e squared nz minus nz plus. This is the nz on scri plus, and this is the nz on scri minus. So you know, this soft piece had a scri plus and a scri minus. Right. So this is the this should be your definition, and then you can just check that if I just consider insertions of Jz into an S matrix, where with this notation, I'm thinking of a correlation function in a CFT, and on the S matrix side, I'm thinking of an amplitude which has these O1, O2 particles to On that these O's satisfy, and Jz is just this operator over here. You can just go ahead and check that this satisfies exactly the Kac-Moody algebra, the Kac-Moody Ward identity. And then you can do double soft limits, and you can check that it also satisfies, in the non-abelian case, it satisfies the Kac-Moody algebra with level 0 at tree level. One loop calculations have not been done, but it's expected to modify that result. Okay, so then in exactly the same way, you want to construct the stress tensor, which is going to be associated to diffeomorphisms, boundary diffeomorphisms, so diffeomorphisms on the sphere. So we do the same thing. We look at QYS, which, let me recall, was just this, YZ bar, what is this, DZ cube, N1 Z bar, what is Z is match up? Yeah. Wait, that's not right. It's a YZ. And this, I'm just, again, just defining the zero mode. So remember, this is the thing that generates the subleading soft graviton. So again, if I want to construct a stress tensor, and here I'm not writing it, but you really also have the contribution from scri minus. So if I wanted a stress tensor that generates this, how is that defined? That's defined as a contour integral of YZ DZZ. And this can be written as integral D2Z YZ DZ bar DZZ. So clearly, this should be equal to this. So this gives you an integral equation of TZZ in terms of in terms of this quantity, and that you can just solve the integral. You can invert the integral on a sphere. And so note that unlike in the Kac-Moody case, where the current was just local in terms of the soft operator, the stress tensor is not local in terms of the corresponding soft operator, but takes some this form. It's a non-local relationship between the soft operator and the boundary stress tensor. And then I'm not going to go into it. You can just check. This is much more work than this case. But you plug in this operator. The insertions of this is given by the soft theorem. And remember, there's an angular momentum operator, which is some differential operator. So you have to work all of those details out. And then the insertions of TZZ take the usual form.
Is it possible to compute the operator product expansion of TZZ itself?
Yes, and it's just the usual one, but with c equal to 0 at tree level again. But subleading one gets us just like this case in the non-abelian theory. There's a one loop exact correction, which has not been worked out actually. So even the stress tensor gets modified. So the one loop correction to the stress tensor has been worked out, but the 2-point function of those one loop corrected stress tensors have not been worked out.
And what do you expect it to get a positive central charge of this number problem?
So here's the question. The point is, in flat space there is no length scale. So you have G Newton, but then what else what would the central charge be? Right? If there's nothing else to make a dimensionless number. So either it's 0. There was a paper by Cliff Chung and Sundram and De La Fuente where they did some alternative calculation and they got something like G Newton times the infrared cutoff. So some
Zero infinity.
yeah. So it's 0. That's the only thing it could be.
Or it could be 1.
Yes. But I want to say actually this non-local relationship, it may not look like it, but this is just a shadow transform. If you know CFTs, if you've done a little bit of CFT, then there's this operation that's a non-local integral operation on conformal primaries that you can do, which is called a shadow transform, which maps a dimension delta operator to a dimension d minus delta operator. So this doesn't quite look like it, but it's exactly that. This guy has dimension 0 and w bar 1. The way to kind of check it, as I said, remember delta is basically omega del omega, and this operator generates the order 1 piece in the soft expansion. So it has dimension 0. And so the shadow transform would give you something that has dimension d, which is 2. In fact, this also, we wrote a paper recently which generalize all these results to higher dimensions where the shadow transform becomes obvious. I mean, here it's not. But there's a reason to not be surprised by that at all. Because I did mention that this ADS foliation at some point, right? So another way to kind of study this entire problem that I'm discussing here is to kind of foliate Minkowski space into these ADS slices, then do a KK compactification. You have an infinitely, like a continuum tower of fields, and then you can attempt to use ADS CFT on the ADS slice once you have KK compactified. So it turns out that the 0 energy modes turn out, when you KK compactify them, end up being massless fields on the ADS slice. So in particular, this NW bar W bar, the subleading mode, becomes a massless spin 2 field on the ADS slice. Now you use ADS CFT, the dual current to that is the stress tensor, as we know. And the stress tensor is the response. This NW bar W bar is the source. And in standard ADS CFT, the relationship between source and response is that of a shadow transform. So that's another way to see why this kind of had to be the case if you analyze this from this perspective. Same thing for the soft mode also, for the soft photon mode. Okay. The L of ADS3 here will just be tau. It will be associated to the non-compact parameter.
You don't really have another, I mean, ADS3 you have like L by G as well.
Yeah. You don't really get certain. Yeah. Okay. Any more questions? I'm going to talk about black holes now. Okay. Excuse me.
Right at the beginning of your talk, you talked about how it could be that the symmetries have implications for correlators that don't involve any soft.
Yes.
Is there any example?
So that hasn't been worked out except for this back of the envelope calculation that I mentioned that I've done with no real justification for some of the assumptions that I made. These are these null state relations. So you get this Kac-Moody algebra at level 0. So just let's say take an example and study SU2 at level 0. Now SU2 at level 0 has a null state at level 2. So the moment you have a null state, this just means you can take any correlation function with any operator, and then you just put in the null state there, and this has to be 0. So this should give you some constraint. And this null state is typically written as a sum of some of these operators. Right? That's with some coefficients.
Yes.
Right? And so this tells you that this gives you a certain constraint on some bunch of 4-point functions.
Okay.
Some constraints of this form. And you can just use that to derive the Park-Taylor formula, for instance. There's a very kind of a, you can show that the 4-point MHV amplitude plus plus minus minus is given by the Park-Taylor formula. Exactly. So that's an example of, I suppose that maybe that's a trivial example, but it really hasn't been studied beyond that. Largely because, as I said, when you say null state, you mean null with respect to a certain norm, which means there's an adjoint. This is a purely Euclidean CFT. We don't even know what the correct definition of adjoint is. So you shouldn't even really trust this point that I've derived here, because we don't even know what adjoint should be defined as and how to define norms of states and that sort of things.
Even standard CFT is radial quantity.
Yeah, but those are all kind of, you get that by really thinking that in the back of your mind you're thinking of a Lorentzian CFT, and there's an adjoint definition there, which you're then Wick rotating to Euclidean, and then that's what it means.
Inherent Euclidean where you take all the operators of the algebra, not that you take data and it's just
I see. Okay, maybe that's the one. Yeah, we haven't thought about this, but this is a very important, certainly a very important and interesting thing to think about.
That is the norm in which principal series representation is observable.
Yeah, I see. Since you mentioned principal series, I will mention that. So another way, as Shiraz did mention one thing, that there's one, maybe in a different context, is like another way to think about this is that when I do scattering, you do plane waves, right? What are plane waves? They are eigenstates of box of the Laplacian, which are also eigenstates of P, right? That's how you construct the plane wave basis. Clearly, for our construction, we want to make manifest Lorentz invariance. So we want to find solutions to the Laplacian which have certain nice scaling properties under the rotation generators. So we wanted to have a specific delta and a specific spin and a specific weight delta, right? That's what we would like, and those are the correct sort of in and out states we would like to scatter in order to have a CFT nice CFT description. But then you have some solution, but the ones we want to pick are the ones that are complete in the sense that I can expand the plane wave basis in this basis and back and forth. And it turns out when you impose those conditions, the ones that you get is precisely the principal series representation. So it seems that in Minkowski space, the physical representations that you're getting are the principal series representations. So yes.
What does this translate to in terms? I mean, one natural thing to do is a spherical decomposition
Yeah.
of your waves. You work in spherical harmonics and so on.
Yeah.
And those will carry definite angular momentum.
Yeah.
And you're saying that those waves correspond to principal series representation? Or some Fourier transform?
Those waves. Yeah, exactly. Yeah. So that's an interesting fact that's very recently been discovered, so people haven't really thought yet much about that. But it does seem like the principal series representations are the ones that are important to look at, and maybe now that you're saying that, I should probably use this notion of Euclidean adjoint to have some unitarity. So it's going to be very different from, so for principal series representations have delta equal to d over 2 plus I lambda. So they're not real, the scaling dimension are not real, but it's d over 2 plus I lambda. And so you have to start considering CFTs with those. They're used in Bootstrap, but they're all used as tools for computation, but they're never interpreted as physical representations that are.
Roughly the point is that when you take the complex conjugate, you get d, so d over 2 minus I.
Yeah.
And together they give you the correct dimension so as to have a scaling variant norm.
Yeah, I see.
The d weight cancels in a way.
The only problem I had with that, so this is something that is confusing me, is that the stress tensor does not lie in principal series representation, right? It has dimension d. But the discussion is suggesting that all energetic modes should stay in d over 2 plus I lambda. But then because you have this continuum limit where I can take energetic operators and take omega to 0 and then get the stress tensor, it seems how can it be that I'm sitting on the principal series and then take a continuous limit, and then I suddenly get a stress tensor which is sitting at d. So I don't understand this at all. So you could have, for instance, thought that it works in 4 dimensions where principal series is 1 plus I lambda, and then the Kac-Moody current lives precisely at lambda equal to 0. It turns out that's how it's actually working. So there you can think of the soft photon limit, and it works out perfectly because it happens to live, the current happens to have dimension 1, which is 1 plus I lambda, which is in the continuum limit of 1 plus I lambda. But then I don't know what to do with the stress tensor, even there. Okay. So yeah, that's just a comment I had to make about principal series. They seem to be important here.
And so you translated S matrices to correlation functions in some way in this putative conformity theory?
That's just a rewriting. It's nothing new. I'm just, in essence, I'm defining a correlation function by saying, in order to compute it, you have to compute this S matrix. So it's just a
good.
Yeah.
So there's some transform of the S matrix that gives you the correlator?
Mellon transform.
Okay.
Yes.
So now what happens, so suppose I take a unitarity relation for the S matrix,
Yes.
and that will give me some equation for the correlator.
Yes.
What equation is that? Is that a familiar equation?
I don't know. Again, an interesting question on the to-do list. Yeah. That would also maybe tell us what the correct notion of adjoint should be.
I think that would come directly.
Exactly. I think that's right.
The bulk current will be directly. In one case implies reflection probability on the cylinder, in this particular, that it would imply.
And the equation is something like S minus S dagger is equal to SS dagger. This would translate to
Basically.
some statement
Yeah.
about correlation functions. Is that a familiar kind of unitarity condition correlation?
Yeah, that is on my to-do list. As anyway, interesting question. Okay, okay, okay. Let me now talk about black holes. I won't have much new things to say because I've already said all the interesting things, and I just have to basically apply those ideas to black holes. And but it might lead to some interesting thoughts. I wouldn't say so. In particular, it modifies the argument of the information paradox, and pulls into question 2 of the assumptions that the information paradox makes. That's not to say that it resolves it in any way, but it certainly modifies it in some way, and it's still a lot of work is left to check, how much it modifies. Does it modify it enough to, basically solve it up to details, or does it not do anything at all? But let me at least point out what new things it might have to say. So the basic idea is, so what is the statement of the no-hair theorem? The statement of the no-hair theorem is that a black hole is completely determined, the metric of a black hole is completely determined by knowing its mass, charge, and angular momentum up to diffeomorphisms. And people often reject this statement of up to diffeomorphisms because they think it's trivial. But the idea is that, as I've now pointed out multiple times, there exist diffeomorphisms which are physical and whose charges can actually be measured. And for instance, the super-translation, super-rotation charge, they can be measured by this memory effect. In other words, you shouldn't take this up to diffeomorphisms trivially. This should in fact tell you that black holes have infinite amount of hair. They have mass, charge, and angular momentum, but they also have an infinite amount of super-translation charges and an infinite amount of super-rotation charges, all of which are in principle measurable. So now what does this do for the information paradox
What is the dimension of the pattern for loop?
of BMS?
Yeah.
I don't know.
Is it not or
No, so super translations are all abelian. So there's an infinite number of commuting generators right there. Yeah. Yeah, yeah. Okay, so the statement of the information paradox is, very loosely stated. You create a black hole with a initial pure state, and eventually it evaporates. And Hawking's argument tells you that the Hawking radiation that it evaporates out to is mostly thermal. And so then the question is, how can you get a thermal state in the final state when you started with a pure state initially? This violates unitarity. So in particular, where did all the information that was in the pure state go? So I did say, for instance, that the Hawking radiation is almost thermal. It's not fully thermal because there is still it does have some correlation. And this was, of course, this is not new. We know, for instance, we expect that energy would be conserved. So we expect that if a certain energy E is radiated into the Hawking radiation, that the final black hole will have, the mass will be m minus E, right? So for instance, clearly the mass of the black hole is correlated to the radiation, the Hawking radiation. So which is the global super translation is fixed. In other words, also you have the other 10 in total 10 Poincare charges. That conservation we always expect to be true. But we usually used to think that that's not going to solve the information paradox because that's just like 10 equations that the Hawking radiation has to satisfy, whereas you in principle have a very large amount of information in the initial state. So that's, even if that's true, that's not going to solve what we have here. But this all changes really because now we have an infinite number of charges that should also be conserved in exactly the same way. So the Hawking radiation should have an infinite number of super translation charges and an infinite number of super rotation charges, all of which when computed should be equal to the super translation and super rotation charge in the initial state.
information that when you used to be more?
I don't know the answer to that. Is that right?
You are saying that the superrotation charge need natural state. That sounds
Well, I'm saying, yeah, well, maybe I am saying that because actually Shiraz mentioned this yesterday. So when I'm doing S matrix calculations, for instance, even if I account for this vacuum, right, there is a unique vacuum state corresponding to every given hard state. It's a given hard energetic kind of mode. There's a unique vacuum state which kind of satisfies all the constraint equations. So I can do it reverse. And what is the super translation charges computing? They're measuring the soft states. They're measuring exactly what vacuum I'm sitting in. So if it is true,
so in other words, you don't expect all the states to be just related to super translation. There are different multiplexes which you have to realize. Therefore, it's not that all states related to one and the other multiplex. You have to look at multiplex based on different channels, and that will be independent apart from.
yes, but I'm trying to say that, let me see. You can have many different hard states. You can have, of course, you can have an infinite number of hard states, but you can also have an infinite number of soft vacua because their functions work. And in particular, for a given hard state, there is a unique soft state. I'm going to motivate this, but I don't know this.
All charges to 0.
Which will set all charges to 0. Exactly. Right? I'm going to write down some equations to motivate this. This is not, I don't know if this is generically true, but in a particular example, I can argue that this is true. So for a given hard state, so you need these charges to be conserved, right? So simple example, let's take that my initial charges are all 0. Initially, all these super rotation, super translation charges are 0. So finally, that must also be true, right? So that means that finally I have some hard state and I need the total rotation charge, hard plus soft, to be equal to 0. This will show you that for a given hard state, the soft state is completely fixed. So if I can measure one of these soft charges, then that tells me exactly what the hard state is.
That is saying that you have precisely the amount of soft generators as soft charges. Question is whether the hard state has any more information.
Yeah, so I'm saying for every hard state, there's a unique map between hard states and soft states, right? So if I know what soft state I am in, then that also tells you what.
In one direction, not the other direction.
I think the ambiguity Abhijit is talking about is collinear hard states. Suppose you've got two photons going in exactly the same direction.
Yes, yes.
Then
Is that a difference? Different?
that will give. It's only the sum of those two that will contribute to the soft stuff, right? Because the soft stuff is direction by direction, but if you have
Yes.
three photons going in the same direction, it's only the sum of those charges that contribute to the soft stuff, right?
Right, right. Probably
So,
that's true.
if you exclude complete, if you exclude complete collinear stuff,
Yes, yes.
completely, then it looks like it goes the other way around. If you assume there's only one graviton per direction, then knowing the soft charge, you can reconstruct the momentum of that.
Yeah, but that's like reducing the Fock space to one particle.
Right.
Yes.
That's a huge reduction.
That's a huge
Yes.
reduction. I agree.
Yes. So collinear, by the way, collinear states have their own interesting properties that have not yet been studied. And there's a guess that even there is a way to distinguish between collinear 1 to 2 particles. But not. Okay, yeah, these are all extremely valid arguments. So as I'm saying, I'm obviously not going to solve the information paradox in the next half an hour, but I'm just mentioning a few new things that you have to think about. That's all. Anyway, so that's just the basic idea that
So there's also flavor in this.
yes.
That of course is totally blank.
Yes. Yes. The flavor indices you could also measure.
How?
No?
I thought your soft charge cared only about the momentum.
Oh yeah, you can't. Yeah, the soft charge won't. But no, that's right. Yes. Yes.
What is the black hole? Perhaps this one, the major data, the black hole and radiation.
But suppose I wanted to know.
There's separate contribution for that.
I mean, flavor is also separately.
No, but you want to know which flavor particle came out in each direction.
Yeah.
Total
right.
flavor is different.
Yeah.
But there's much more information than that.
Okay. So all I'm going to say in the next few minutes is to basically argue that. Well, firstly, argue that black holes in fact do carry supertranslation charges, and explain how to even create physically a supertranslated black hole.
But just one second before. I just want to get the basic physical idea of this correlation. You're worried in terms of charges, but I could be in a context like ADS where they don't exist, and yet I have issues. So so it seems to me that your basic idea is that there is a strong correlation, as you say,
Yeah.
between the hard stuff and the soft stuff.
Yeah.
And perhaps then what you're now suppose you've got a black hole that has lived for a certain lifetime, whose lifetime is, let's say, T. Let me define by soft stuff anything that is longer wavelength than m times t, where m is 0.001 or something like that. Okay? Now, it seems to me that you could try to take the Hilbert space of radiation and break it up into soft plus hard.
Yeah.
And then you could try to trace out the soft stuff.
Exactly.
And maybe what you're claiming is that if you did that, then you would get a genuine thermal density difference.
I was going to do that exact calculation. Yes. Yeah. Not now. In a bit. I was going to do exactly that. Yes. So if you assume that the soft state is uniquely determined by the hard state, then you get a thermal density matrix when you trace it out as expected. That's what I was simply going to show. Now that assumption is strong, and you would have to justify it by other means, but
We could just check whether there's enough information in soft mode,
yes.
where soft is defined as lifetime to lifetime by 1,000.
Yeah.
Have you,
Yeah.
that's an easy calculation. Just the entropy of soft stuff in that box. That's an easy calculation too. Presumably it's larger than the entropy of the black hole.
I haven't done that.
I think Ashok and I once discussed it. These are a number parametrically larger.
Okay. Okay. Let me first justify some of this maybe more robust claims. At least classically, I would like to argue that there is a difference between the Schwarzschild solution and a super-translated Schwarzschild solution, a physical difference that can be measured. And then let me also argue that there's a physical way to construct super-translated black hole solutions, in the sense that what it's going to be is that if I give you a Schwarzschild solution, some Schwarzschild black hole, and I send in a certain null shock wave with a particular sort of angular profile, and it falls into the black hole.
I remind you that our attention spans have a finite.
Yes.
Time.
Yes.
Time bound.
Yes. As I said, I won't have much to say because it's all a lot of very vague. If anything, this is the only thing that I would be able to say concretely. Okay. So just very quickly, so you have the Schwarzschild metric, which is just minus V and this V is just 1 minus 2 MB over R, and this is just G times the mass of the Schwarzschild metric. And for this guy, you can work out this actually exactly for all R. You can actually perform that integral, and then determine the infinitesimal it's exactly this with no corrections. And then you can just ask what is the super translated metric. So the new ds squared to just linear order is just ds squared plus. Okay, so I won't bother writing this, but you can work this out. It's just a Lie derivative with respect to this psi, and you can work out what it is. So that's what I mean by a super translated Schwarzschild black hole. The way, of course, you would measure this is because super translations is an abelian group, you can't measure a super translated black hole by measuring a super translation charge. That's just going to be 0. You'd have to measure a super rotation charge. So the super rotation charge for this black hole, you can evaluate it by essentially kind of sending a observer, well, ideally sending an observer that moves along the horizon, but also very close to the horizon is good enough. And you can measure this because they're going to measure something that looks like this. So the observer is going to choose a particular y for which he wants to measure it, and then he can read off the function f. So that's how he's going to measure it. So this is clearly a physical black hole, but how to actually physically construct it? So again, let me not go into details, but just tell you that the physical stress tensor that you would have to use to solve is something that looks like this. And just to ensure that this is conserved, you have to also put in something.
What, this is a matter?
Yeah, this is matter. So I'll explain. Yes. So here I've just written down a Schwarzschild black hole.
Yeah.
This is some solution,
Yeah.
and this is how you would measure it. Here I'm trying to explain how you would create such a black hole. So a Schwarzschild black hole you can create, as you know, using the Vaidya kind of thing. You just send in a null shock wave with some particular mass, and that after you do that, that creates for you a Schwarzschild black hole. Here, this super translated black hole you can construct by sending in this shock wave. This is also a null shock wave at a particular point, but it now has some angular profile given by this f, and you need to add in this so that it's conserved. So that's what all you would have to do. Send in this null shock wave, and I won't prove it, but
You just computed the charges of that.
yeah. So plug in, solve Einstein's equations with this t, and you'll find the super translated metric. So this is just a very quick, maybe not surprising, just a quick way to show you that these are physical black holes. There are physical ways to create them using some sort of sources.
And the way you guessed that was just go to Stry minus, compute the charges of this stuff,
Yes.
and then therefore.
Well, the way I guessed that was to take the solution and compute the left-hand side of the Einstein's equation, and that
But
just
I
gives you
don't
t.
understand why Einstein equation has the left hand. If it's a diffeomorphism, it's just that.
Oh wait, yeah. What did I do now? What's that? Yeah, sorry.
I mean, presumably what
Yeah.
you're saying is you send this, you wait a long time and then you get it.
Yeah, absolutely.
So presumably what I thought you were going to say was that on Scry minus, you can compute the soft charges of this
Yes, you can. Yes, that's certainly also. Yes.
and check
And you
that
you
matches
get
the
this.
soft charges of that.
Yes.
So if it produces a black hole, it has to produce that one because
Yes.
it has the right charge.
Absolutely.
What?
You're taking an involved solution and then it is translated to the correct process.
Yeah, maybe
Yeah,
another way of doing it would be to take a standard Verdier solution and transform the.
Yeah. Just do a super translation on the TVV of. Yeah, I'm not saying anything shocking. I'm just trying to.
No, I
Yeah,
understand.
yeah.
You're making the point that you could actually create this.
Yes. Okay, so this establishes that super translated black holes exist, and they can be measured and distinguished from non-super translated black holes. Rather, that's not quite the right statement. You can distinguish between whether a super translation has happened. You can't really say whether a black hole is super translated or not. You can say whether it had it before. Oh no, that's not right. Sorry, super rotations because it doesn't commute. That the comment I was making was about I was thinking of gauge transformations. You can also do the same thing with charged black holes. So Riemann-Nordstrom black holes also have an infinite amount of large gauge charges, and you can try to construct those.
So maybe they could measure it, measure it also soft charges, sitting at strike plus
No. You can for the black holes you have to do the horizon measurement. So you can like imagine an observer ideally going along the horizon, and he can choose a particular y, measure the super rotation charge, and then extract the f. You can do horizon charge measurement. So all of these charges exist also on the horizon. The point about why these charges are non-trivial is that because Scry plus was really a null surface. At the end of the day, it boils down to that. So horizon is just another null surface, and you can compute all of these charges also on that. I mean, it simplifies the Scry plus because it's far away at infinity. That may not be true on the horizon, and it might be more complicated. But
I think this double analysis that you did for the horizon test, and you did
yes, you can do it. It'll just be more complicated because the horizon is at a finite proper distance away. So things don't die off or anything like that. More things. Yeah. That's that. So in other words, I'm saying that if I have a black hole of this form, right? Right. So then I send in some data over here, which has a certain charge. But this data can either fall into the black hole or it can go out. So the future charge, I need to measure the charge on Scry plus, but I also need to measure the charge on the horizon. And I would measure the charge on the horizon using this. So in particular, if I send in a super translated sort of data, you can get a super translation on Scry plus, but you can also get a super translated black hole in the bulk. And you would have to measure both of them and then the sum of those two things would be conserved, would be equal to what I sent in, as expected. Of course, this, you know that this is true for the global charge or global energy. That was not new. All I'm saying now is that it should also be true for these infinite number of charges. Okay, let me just end with this very brief thing that Shiraz mentioned, and I'm just literally going to write 2 sentences, and I'll be done. So what really happens with the information paradox is that I send in a certain in state, and Hawking's argument is that at the end of the day, you no longer get you get a density matrix as opposed to a pure state, and this density matrix is something like, where here I'm denoting H as some hard energy. So I'm measuring the Hawking radiation, which are all hard states. They have the usual thermal particle, the thermal spectrum. What I would say previously, I suppose people might have expected is that unitarity says that there is an S matrix, which means that this is what might be expected is that there's some pure state, there's an S matrix which unitarily maps this in state to some out state which takes this form. I mean, this doesn't match with that. But so the actual suggestion is that the hard state is always accompanied by a soft state, and this total thing is psi out. And of course, psi out is still a pure state. And as Shiraz was mentioning, is that we might want to trace out S alpha if you're not measuring it. And if I assume that S alpha, S beta is delta alpha beta, this is the assumption that for a given hard state, there's a unique soft state. Because alpha labels the set of hard states. And I'm assuming that they're all unique and they're orthogonal. So if I make this assumption, then you can just basically show that the final density matrix you get is just sum over alpha C alpha squared S alpha. Right? So clearly I can recover Hawking's thermal density matrix by setting C alpha to be just square root of rho alpha times a phase. The crucial details of all is to compute the phase, and that would actually be the thing to solve the information paradox. But it doesn't. Anyway, this was just a kind of a brief idea to say how it might happen that if the soft modes are highly correlated with the hard modes, and here it means that they're uniquely determined, then tracing them all out, there is a possibility to explain the thermal nature of the Hawking radiation.
Just to say again, that suppose the lifetime of a black hole is T,
Yes.
then the evaporation process doesn't know whether it's in a box of 10 T.
Yes. That's right.
So by soft, you can't mean literally. Because a box of size
Yes.
SC will kill the literally zero.
Yes. Yes.
So it's some,
Yeah.
some band of energy.
Some band of energy. Okay, so this is what I like. This discussion with asymptotic symmetries has to say about black holes. So I'll end here, and I'll just say I think it's a very rich subject. With you guys have asked me a lot of questions, and I've almost said I don't know to most of them. There's a lot of interesting questions and a lot of new things to do. So it's exciting to work in this. It would be great to have some of you also work on it. Thank you.